segment trees with point updates from the ground up. I was trying to solve LeetCode 3161 block placement queries, but every time I built a solution, there was some n-squared component that made it time out. I thought I was being clever by defining infinity as one higher than any number we cared about, by scanning the maximum x values, but it wasn't enough. I needed to learn about segment trees. This is going to be a generic introduction to segment trees with point updates, not specific to that exact problem. One quick aside. In that problem, the obstacles sit at infinitely thin points on the number line, which honestly bugs me a little. Personally, I'd have made each division a block of length 1. Same test, less weirdness. The nice thing is, in the generic segment tree we're about to build, that's exactly what happens. Every leaf is a single cell, a block of length 1. So we'll think of it that way. Here's the tension a segment tree resolves. Say you have an array and you want two things. Ask for the sum over some range and occasionally change a single value. A plain array gives you instant updates, but a range sum costs order n. Prefix sums flip it. Instant range sums, but one update forces you to rebuild everything, again order n. A segment tree gives you both in order log n. Let's build one over this 6-element array. The leaves along the bottom are the original elements, indices 0 through 5. Each internal node stores the sum of the range beneath it. The root covers the whole array, indices 0 to 5, and stores their total, 17. Its two children split the range in half. The left covers indices 0 to 2, summing to 8. The right covers 3 to 5, summing to 9. 8 plus 9 is 17. Every parent is just the sum of its two children. Keep splitting until each range is a single cell. Those are the leaves. One block of length 1 each, holding the original values. Now a range query. Suppose we want the sum of indices 2 through 4. Instead of touching every element, the tree answers with just a couple of pre-computed nodes. The cell at index 2, value 5, and the node covering 3 to 4, value 7. 5 plus 7 is 12. 2 nodes instead of 3 elements, and on a big array, it's a handful of nodes instead of thousands. Why is that fast? The tree's height is about log n, and any range breaks into at most a couple of nodes per level. So a query visits order log n nodes, no matter how big the array gets. Now the other operation, a point update. Let's change index 4 from 4 to 9. First, we change the leaf itself to 9. Then we recompute its parent, the node covering 3 to 4. 3 plus 9 is 12. Up again, the node covering 3 to 5 becomes 12 plus 2, 14. And finally, the root. 8 plus 14, 22. Notice we only touched the nodes on the path from the leaf up to the root. Everything else was left untouched. That's the whole idea. Both operations walk a single path of height log n, so a query and an update are each order log n, and building the tree once is order n. Back where we started, the reason 3161 kept timing out is that the naive check is order n per query, and with up to 15,000 queries, that's n squared. In other words, TLE, swap in a segment tree, and each query drops to log n. That was the missing piece. Thanks for watching.